This is our first video on the kinematics of simple harmonic motion. And what we are going to try to demonstrate here is that the math of uniform circular motion and the mathematics of simple harmonic motion relate to each other. And what I'm going through here is basically what could be class notes. And I'm going to cut a few corners for the sake of the video, but I want to just give you the general feel for what's happening. So here we have an object that is in uniform circular motion. And I've labeled 4 specific points. I'm going to call those the compass points. And then there's one point down here. This vector represents the velocity vector. And this one towards the center, of course, that's the acceleration. That's the centripetal acceleration if we're in uniform circular motion. So around the horn here, if we were to draw similar velocity vectors, I'm going to draw these velocity vectors in red, and I'm trying to draw them tangent to the circle and of equal length with this one that is given here, because we're in uniform circular motion, so the speed is staying the same. So there we have the velocity vectors. The acceleration vectors I'll draw in green, and those are going to point towards the center, and they're going to be hopefully the same length as the one that is already shown. Something like that. At any point around this circle, there is a combination of x and y velocities. For this one that's shown in the lower left here, this one we can see, I'll draw it in blue, has a vx velocity vector right there and a vy velocity vector that goes like that. There's vx for that particular point, and here is vy for that particular point. Similarly, for the acceleration, I'm not going to draw those in, but the acceleration, this acceleration that is shown, you can see is not entirely in the x direction, but it's not entirely in the y direction. It has some component of both. On the other hand, at the compass points, one component is entirely zero. For example, down here, what we might call south, you can see that the velocity vector is entirely in the x direction. There's no y velocity there. Similarly, the acceleration down here at this south point is entirely in the y direction. If I were to kind of accentuate the x values, that's an x acceleration on the left. Here at point north, there is an x velocity. Over here in point east, that is an x acceleration. And right here is an x velocity. Here's an x velocity. I'll just put black arrowheads there on the x's. Maybe I should circle those. Shall I circle them? That's an x value. That's a velocity. That's an x acceleration. That's an x velocity. And that is an x acceleration. And so what we're seeing here is that what I might call the north and south points, the acceleration in the x direction is 0. Same with down here. The acceleration in the x direction is 0. The velocity in the x direction, let me use an absolute value sign, the velocity in the x direction down here at point south is a maximum. Same thing here at point north. The magnitude of the velocity in the x direction is a maximum there. What about at points east and west? At points east and west, we have the acceleration in the x direction, let me put an absolute value sign, is a maximum, but the x velocity is 0. Same thing on point west here. The magnitude of the x acceleration is maximized, and the x velocity is 0. So if we can look at the things that I've drawn in black here, this is a little hard to see. What we're seeing is that the velocities are 0 at points east and west, but the accelerations are maximized. Right here at points north and south, The velocities are maximized, but the accelerations in the x direction are 0. We're only worried about the x direction. We could talk about the y direction, but we're going to use this in doing a little bit of math with simple harmonic motion. Now, the last thing we need here is this point that is in the upper right here. That has a certain x coordinate, doesn't it? And a certain y coordinate. And its x coordinate is, if this is the origin here at the center, is equal to that length right there. And if I call that angle theta, then isn't it true that x is equal to r times the cosine of theta? We're going to see that again. All right, we'll skip ahead a little bit to this next part. Let me zoom in here a little bit so you can see this a little bit better. There we go. Velocity, as we know, is displacement over time. So angular velocity is angular displacement over time, which is the final angular position minus the initial angular position divided by time. And if we rename theta final as just theta and theta initial as phi, so if I call theta initial phi, and if I call theta final just theta, we get that. And if we solve that for theta, then we're going to get that theta is phi plus omega times t. Now, the equation we just wrote, let's combine those. X, we just said on the previous page, was r cosine theta. Well, theta is this thing here. So x is r cosine phi plus omega t. For any time, any particular time, we can find the x coordinate using this equation. That's an equation for x position versus time. If we differentiate it once, then we get an equation for the x velocity versus time. And if you remember on the previous page, we were talking about, oh, the x velocity is changing as this thing goes around. Similarly, if we differentiate it a second time, we're going to get an equation for the x acceleration versus time. One more time, as we talked about on the previous page, the x acceleration is changing as this thing goes around. So let's do that. Let's differentiate this equation once, and then let's differentiate it a second time. We would pull the constant r out front here, and then when we differentiate cosine, we get the opposite sign of the thing. We're going to have to use the chain rule here. Then we have to differentiate the thing inside here with respect to time, and that's going to just give us a constant of omega out there like that. If we differentiate it a second time, that's going to give us an acceleration time curve, and let's keep these constants just like they were, negative r omega. Now, when we differentiate sine of something, we get the cosine of that thing. And then by the chain rule, we have to differentiate what's inside the parentheses with respect to time, and that's going to give us a factor of squared here in the front. These are the equations for simple harmonic motion for basically a mass going back and forth on a spring. All right, let's finish with this page then. As we know, the maximum value of sine or cosine is 1. Given the fact that the maximum value of sine or cosine is 1, then the maximum x value, the maximum value that x can have, is going to be r, because the maximum value of cosine, we said, was just 1. So the biggest that x could be is r. And where does that occur? That occurs, according to my diagram here that we drew on earlier, at points east and west. What about the maximum velocity? Well, the maximum velocity, let me put this equation here in front of you. Here we go. There's the velocity equation. The maximum that sine can be is 1, so the maximum velocity has a magnitude of r times omega. And where did the maximum velocity occur? Let's flip back here real quick. You see that? Right at the top. Vx is a maximum there, and where else? down here at the bottom. So at points north and south, Vx is a maximum. All right, last one then. Where's the acceleration of maximum? What is its magnitude? Look at the equation at the bottom of the screen here. Cosine, the maximum it can be is 1. So the maximum value that the acceleration could be has a magnitude of r omega squared. And where does that occur? Let's go back to the drawing that we started with. And you can see there on the left side and the right side, you see how we've circled? Hey, the acceleration is a maximum west and east. There was a lot going on there, and we're going to deal with that some more later, but that will give us a foundation to go from.